To complete our introduction to computer program, we have to introduce one further idea in addition to the ideas that we learnt about last week, namely logic. Before we get onto logic, however, let's first quickly review the two key programming ideas that we learned about last week. Last week, we first learned about variables. We learned that variables are labelled addresses in memory and that we can store values in the state of a variable. We then learnt that functions are used to change the state of these variables. With these two pieces in place, we learned how to draw graphs, interpolate functions, calculate integrals and derivatives analytically, and so on. We can thus write Python programs to plot linear functions, quadratics, polynomials of any order, trigonometric functions, and exponentials, just using what we learned about variables and functions in the exercises last week. Sadly, however, we do not know enough Python to write a program to plot every function of one variable that we might be interested in. One example of a function that we do not yet know how to plot is shown here on this slide. This is the modulo function, which is written using the symbols shown here. F of x here is calculated by replacing the sign of the input variable with a positive sign. In other words, f of x is calculated using the expression shown here, which reads as follows. If x is less than 0, i.e. if x is negative, then f of x is equal to minus 1 times x. If x is greater than or equal to 0, i.e. if x is not negative, then f of x is equal to x. Importantly, when we write x is less than 0 in an expression such as the one we are writing here, this is a logical proposition. This is important as a proposition such as x is less than 0 has a truth value. The truth value for this proposition is 1 if the proposition is true and 0 if the proposition is false. In this case, the proposition x is less than 0 is equal to 1 if x is negative, and the proposition x is less than 0 is equal to 0 if x is not negative. Now, suppose that we want to express how this function is calculated. Modulus is a function, so like any other function, an argument, x, is passed to it, and a second value is returned from the function, just like the other functions that we learned about last week. What happens within the function is somewhat different to what happened in the functions that you learned about last week. The first thing that happens within the function is that the truth value of the proposition x is less than 0 is evaluated. If this proposition's truth value is 1, then y is evaluated as minus 1 times x. If the truth value of the proposition is 0, then y is set equal to x. Once y is evaluated, using whatever method is appropriate, this is then returned from the function. Within programs, we can write functions that exploit the truth values of propositions in the way I have just described by using if-else blocks. A Python code to complete the task illustrated in the flowchart at the top of the page is shown here. As you can see, I have called the function modulo, just as I have labelled the box containing my function at the top of the page, modulo. The variable x in the calling code, the variable z in the calling code can thus be set equal to the modulus of the variable a by calling this function by writing z equals modulo a, just as we saw last week. You will also notice that the function takes a single input argument x, as is indicated in the diagram, and also that the function returns a single value y, just as would be expected based on our flowchart. The decision as to how to compute y is made by the line containing the if statement. As you can see, the logical proposition x is less than 0 that appears in our flowchart appears here. The code shown here is executed if the proposition is true. If the proposition is false, by contrast, the code shown here is executed. Now, I feel I should point out that I would not personally write a function for computing the modulo in this way. As you know from last week, I am all about making my programs as short as possible, because if I write fewer lines of code, I make fewer mistakes. I would thus write a function for computing the modulo like this. Notice that because there is only one line to execute if the proposition is true, I can write that code on the same line as the if and the proposition. Further note that whenever the function encounters a return statement, none of the code that appears after the return statement is executed. I can thus shorten my function even further and remove the else. These niceties aside, let's dig further into the anatomy of these if blocks. Consider the slightly more complicated function called func that is shown here. This function takes one argument x. As we saw in the previous exercise, the actions that are performed by the function are then determined based on the truth value of the logical proposition shown here. Now notice that less than is not the only binary operator that can appear in our propositions. We can use any one of the following set of symbols, namely greater than, less than or equal to, greater than or equal to, is equal to, is not equal to. As I hope you can see, we can easily construct logical propositions involving a pair of variables or a variable and a scalar using any of these binary operations. Furthermore, the propositions that we construct in this way will have a truth value, just as we have seen that the proposition x is less than 0 has a truth value. Once we have constructed our proposition and inserted it into our if statement, we can then write the code that should be executed if the proposition is true. Every line of code that appears after the if statement and that is indented is executed if the proposition is true. In this case, these two lines are thus executed if the proposition is true. By contrast, these two lines are executed if the proposition is false. Once again, it is those indented lines that appear after the else that are executed if the proposition is false. If code appears after an if statement that is not indented, then it is always executed, i.e., regardless of the truth value of the proposition. The return statement in this code is executed if the proposition is true and if it is false. On the subject of this return statement, notice that we are returning two numbers from this function. The function would thus be called as follows. Once it runs, a is set equal to y1, whilst b is set equal to y2. That should be enough Python to complete the next few programming exercises. Before I finish the video, however, I need to explain a bit of the mathematics of propositions so you can complete the quiz on this topic that appears before the programming exercises. Logical propositions also appear in mathematics. The proposition A equals B thus has a truth value when we write it in some equations. Notice also that when we write the proposition A equals B in maths, we use a single equals sign, whereas when we write the proposition A equals B in Python, we use two equals sign. The reason for this difference in Python is that, as we have already established, a single equals sign is used to set the state of a variable in Python. In the quiz and the programming exercises, you will be learning to handle truth tables for logical propositions. When you make a truth table, you take one proposition and write what values a second different proposition takes when the first proposition is true and when it is false. For example, as shown here, you might consider what values the proposition A is less than or equal to B takes when A is equal to B and when A is not equal to B, as shown here. Before I reveal what numbers appear in the truth table, note once more that the symbol for less than or equal to that we wrote when we write mathematical expressions is different from the symbol that was used within Python. This digression aside, we can now fill in the table. If the proposition A equals B is true, then the proposition A is less than or equal to B must also be true. If by contrast the proposition A equals B is false, we do not know whether A is less than or equal to B, as A is not equal to B. As if A is not equal to B, it may be less than B, in which case the second proposition is true, A and B, but A and B are also not equal if A is greater than B. In this second case, the second proposition, i.e. that A is less than or equal to B, is also not true. We thus cannot know the truth value of A is less than or equal to B if we are just told that A is not equal to B. Hopefully that is straightforward enough and enough information for you to complete the questions in the quiz. I won't tear you away from that for much longer, and we'll just finish by reviewing everything we now know about the three elements from which we can construct computer programs. We have established that variables are labelled addresses in memories and that we can store the values in the state of a variable. We have established that functions are used to change the state of these variables, and last but not least, we have just learned that logic makes the behaviour of the program dependent on the state of the variables. Good luck with the exercises that follow. As always, ask if there is anything that you need help with.